Okay, so it seems that we are live on YouTube. Let's check here. Yes, we are live. Okay, so let's start the seminar. So, good afternoon, everyone. Welcome to our weekly colloquia. And today we have the huge honor of having Professor Jill Tarter with us. So it's a huge honor for our institute and for me personally, as I work in the field of astrobiology. So I'd like to public make a public thank you, Jill, for setting the foundations of this field, so people like me and others would be able to work on this field right now in this very exciting moment that where in which we are having images of exoplanets and finding possible biosignatures in Venus. So thank you very much for all the hard work you put in the field of astrobiology. It's a great pleasure to have you here. So just to give you background, a quick bio of Professor Jill. She is an emeritus chair for SETI research at the SETI Institute in Mountain View, California, and serves as a member of the board of trustees for that institution. She received her Bachelor of Engineering Physics degree with distinction from Cornell University and master's degree and a PhD in astronomy from the University of California, Berkeley. She has spent the majority of her professional career attempting to answer the old human question, are we alone? By searching for evidence of technological civilizations beyond Earth. She served as a project scientist for NASA's SETI program, the High Resolution Microwave Survey, and has conducted numerous observational programs at radio observatories worldwide. She's a fellow of the AAAS, the California Academy of Science, and the Explorers Club. She was named one of the Time 100 most influential people in the world in 2004 and one of the Time 25 in space in 2012. Received a TED Prize in 2019 and 2 public service awards from NASA, multiple awards for communicating science to the public, and has been honored as a woman in technology. She was a 2014 Jansky Lecturer and received the Genius Award from Liberty Science Center in 2015. She served as the president of the California Academy of Science in 2015-16, and asteroid 74824 Tarter 99 TJ16 has been named in her honor. Since the termination of funding for NASA's SETI program in '93, she has served in a leadership role to design and build the Allen Telescope Array and to secure private funding to continue the exploratory science of SETI. And many of you may be familiar with her work as she was portrayed by Jodie Foster in the movie Contact. And her biography, Making Contact, was written by Sarah Scholes and published in 2017, if you want to read it. So, Professor Jill, it's as I said, it's a great honor to have you here. So you can feel free to start with the talk and let us know a little bit more about what astrobiology has been doing in the last few decades and years. Thank you very much for being here.
Well, it's my pleasure to be here. And, you know, Rio is one of my favorite places. My husband and I love to dance the samba, and I had this mystical, magical idea that when we first went to Rio, that the samba would be wafting out of every small cafe that we passed by. Turns out we had to work a bit harder to find the music, but we did and loved it. So it's really my pleasure to be with you. And I think it's important, before we start talking about how we might find them, to set the stage for us, how we fit into this universe. And so I want to start by talking about what we mean by here and now in a cosmic context. So, like many of you, for me, here is here in my house, locked down, working from home because of the coronavirus that we are all dealing with. And in my case, that home is this house here in the Berkeley Hills in California, which is in the San Francisco Bay Area. And from the altitude of low Earth orbiting satellites, we'd see ourselves, or I'd see myself here, the west coast of California, which is currently smoky and on fire. And that, I'm afraid that's the new normal that we're going to be facing because of climate change. But here we are. And indeed, since 1968, when Bill Anders made this fabulous Earthrise photo as he was coming around the limb of the moon, we've been able to visualize ourselves as being here on a planet in the vastness of space. And that, I think, has changed a great many things, and this has become emblematic of the environmental movement in the planet. But we are here on a single individual planet. We can see ourselves as part of a larger solar system. Here, at the end of that arrow, there is a little dot. And in fact, that is us. And the Cassini spacecraft took this selfie of all of us back in 2013. We're here. And earlier, as the Voyager 1 spacecraft in 1990 passed by Neptune, it turned around and looked homeward and saw us here in a sunbeam, this pale blue dot. Indeed, our sun is one of something like 200 to 400 billion stars in a galaxy of stars that we call the Milky Way. And you can see we're not anywhere near the center. We're out here in the suburbs. And although everything that I've shown you up until this image has been an actual picture that we've taken, there is not a way yet to get outside the Milky Way galaxy to look back and take a picture of the galaxy. So this is a spiral galaxy M101 that we think is what the Milky Way galaxy would look like if we could get outside and take a picture of it. And although we can't take a picture of it, we can in fact use radio telescopes to measure it and to get an accurate depiction of the gas and the stars in the galaxy. And this was published earlier this spring of this year. It took thousands of hours of telescope time to construct this image of the Milky Way. But this indeed is the home galaxy in which we find ourselves. So that's here. What about now? Well, when you look at this image from the Hubble Space Telescope, which shows you many, many, many galaxies, these individual patches of light are not stars. They are individual galaxies full of hundreds of billions of stars. And you can see that some of these are fainter and smaller and dimmer, and that's because they are farther away. So we understand that as we look farther from the Earth out into space, we are also looking back in time because of the finite speed of light. So we then need to consider not only here in this big cosmic context, but now. Where are we in time? Well, we find ourselves here after 13.8 billion years of cosmic evolution. And we humans measure our history against this long history of the universe. And our human history goes back not just through the centuries of our families. We trace our lineage back through the thousands of years of civilization and architecture and art and various forms of governance. We trace ourselves back further beyond the millions of years since we evolved away from the great apes. We trace our lineage back beyond the 2.4 billion years during which our atmosphere has been perfused with oxygen, thanks to the efforts of blue-green algae, cyanobacteria. We go back farther than that. We go back earlier than the formation of our solar system, the planets that orbit the sun. In fact, we can actually trace ourselves and our lineage back to a supernova that exploded billions of years ago and polluted the giant molecular cloud in which that star existed. It polluted it with all of the products of nuclear fusion that had gone on in the heart of that massive star, creating all of the elements heavier than hydrogen and helium, all of the stuff that makes you, right? So nuclear fusion is what provided the calcium in your bones, the iron in the hemoglobin molecules in your blood. And so this is really where you came from. And this long story is to make a point that indeed it actually takes a whole cosmos to make a human. And we are intimately connected with those long ago, far away events. We are indeed, as Carl Sagan used to tell us, made of stardust. And we have taken pretty much a millennium to piece together this scientific explanation of our origins. And we are on a road to continue discovery and to continue trying to answer questions about who we are and why we are and whether or not there's anyone else out there. So in my career, there have been two really big game changers, right, in the 20th century. And those are extremophiles and exoplanets. So extremophiles are types of life living in environments which, as recently as when I was a student, I was told that absolutely these environments would be totally incapable of supporting life. Well, that was just a bias, right? That was a bias because when we think about life, or when we thought about life, we thought about ourselves. We thought where we could function. But indeed, life exists frozen in ice, in boiling battery acid, in volcanic environments. It indeed can survive the desiccation and lack of oxygen of space. And life with billions of years of evolutionary adjustment can, in fact, exist in places that would be unthinkable for us. And so we've had to expand our thinking beyond just humans and where we could thrive, to appreciate the fact that life can thrive in much different conditions. And this has been a really difficult philosophical shift to think more broadly about life than just ourselves. And so we now know that life exists in amazing places that we never thought it could. And the other game changer is the fact that we know now that there are more planets than there are stars in the Milky Way galaxy, right? Every star has at least one planet, statistically speaking. And this is a huge game changer, right? Because when we started this search for life beyond Earth, we didn't know about any other planets. But now we know that given the extreme conditions under which life on this planet can thrive, and the huge number of planets that are available out there in the Milky Way, we know that there's a lot more real estate that's potentially habitable than we ever imagined. And so now, this particular time in history is the first time that we can begin to ask and answer the question of whether any of this potentially habitable real estate is actually inhabited. And so we think about looking for biosignatures, right? We can look at various planets and moons in our own solar system, sending humans or robotic explorers to the surface of these worlds to see if we can detect evidence of life. And we can think about looking with telescopes of increasing capability. We can look at the atmospheres of some of these distant exoplanets, and we can look for the signatures of gases that are produced by biology. So if you look in our own solar system, you can see that Earth is significantly different than the atmosphere of Venus or Mars. And it's marked by a chemical disequilibrium. It's marked by the simultaneous presence of molecular oxygen and methane. Now, if you put those two gases together in the laboratory, they instantly turn into water and carbon dioxide. And indeed, that's happening in our atmosphere all the time. But because we have biology on the surface of our planet, we have plants and trees photosynthesizing and producing oxygen, and we have cows producing methane, bovine flatulence, if you wish, cow fart, enriching our atmosphere with methane. We have this very pronounced disequilibrium chemistry in our atmosphere. And so we'll go looking for this kind of chemical signature in the atmospheres of distant planets. And this isn't easy. It really isn't, as we've just seen in the past few days with our own solar system, where when we look at the planet Venus, we see a gas called phosphine in the atmosphere which we cannot easily explain with a chemical network that is abiogenic. And so there has been the claim, although very weak, that perhaps that phosphine in the atmosphere of Venus indicates that there may be some life of some kind in the cloud decks of that planet. Very controversial, not at all well documented, in the sense that perhaps when we try and lay out the chemical network for reactions that might be going on in the atmosphere and the clouds of Venus, we may have left out something, which could in fact mean that phosphine is easier to produce than we thought, and in fact doesn't require a biological microbial source for its presence. But here we are, scratching our heads and looking to do more detailed observations to try and understand what's happening there. So we will try and do this, and it will be harder because they're much farther away. We will try and do this by looking at the atmospheres of distant exoplanets and try and see if we can find that chemical disequilibrium that indicates that perhaps there is some biological source for the gases there. And the other thing we can do, which may be less ambiguous, although perhaps more difficult, is to look for technosignatures, to look for evidence that someone, something, is modifying their environment in ways that we could detect at cosmic distances. I mean, we can detect the Earth and what our technology is doing. We could detect the Earth if it were far away. And so perhaps some other technological civilization might be doing something that indeed we could, if we looked hard enough and had the right instruments, detect and deduce that there was some kind of engineering going on, something that was non-natural. So historically, we began searching for these technosignatures back in the 1960s with radio telescopes. And since then, we've added optical telescopes like the Keck, and we actually expanded the search into the near infrared, looking for these technosignatures. So what we're looking for is something that is engineered versus natural. And here's what we call a waterfall plot. Frequency is plotted horizontally and time is plotted vertically. And all those little dots, all of that snow is natural. That's what nature is producing. But you can see traces in there that are clearly not natural. And this is what sometimes the planet Mars looks like to our radio telescopes. When the Mars MRO or the Mars Express satellites are on our side of Mars, and we see the carriers that they are transmitting back to Earth. And it's these engineered signals that we're trying to find from some other planetary system. So the other important thing about looking for technosignatures is that we have to realize that the search will not succeed unless those technosignatures persist for a very long time. So whatever the technology is that we're looking for, it has to be long-lived if we are to succeed. Because if they broadcast or if they do something that is potentially observable, but do it only for a very short time, then the probability that there will be a technology close enough to us to be able to be detectable, but also lined up in time over the 10 billion year history of our galaxy, so that we coexist both spatially and temporally with another technology. Probability of that happening is very, very small, unless the technology is extremely long-lived. And that's long in cosmic times, not in human times. So it's the reason that Philip Morrison has called SETI the archaeology of the future, of our future, right? If we find a signal, if we find some evidence of someone else's technology, then that means that it's possible for us to have a long future. Somebody else made it through this technological adolescence, the stage in which we find ourselves today. Someone else made it through. There is a way to become a long-lived and stable technology. And so we can find a path to a long future if we work at it and are diligent. So I love Phil Morrison's characterization of SETI as the archaeology of the future. Well, we've been doing this, starting with radio in the 1960s. We've been doing this for, well, when I drew this slide, when SETI was 50 years old. And I said, well, let's consider all of the things that we might have to search, all of the frequencies, the locations, the polarizations, the modulation structure, the power, the sensitivity of our searches, and altogether 9 different dimensions of the search. And let me take that volume that we might have to search through to find a signal. And let me, by analogy, say that volume is equal to the volume of all the world's oceans. And so in 50 years, how much have we searched? And it was pretty sobering, because relative to the oceans, we've actually searched just 1 glass of water out of all of that ocean in 50 plus years. So now 60 years on, students at Penn State did this calculation again, and they calculated the small, it's more like not 1 glass, but 60 years on, it's more like a small swimming pool or a hot tub of the ocean. Still not very much. But the point is that the speed with which we can make our searches is improving and speeding up exponentially, right? And it's primarily because of the exponential improvement in computational capability. And it's also because we've begun building some tools specifically for SETI. This is the Allen Telescope Array in Northern California. It's the first time we've built the equivalent of a large radio telescope by building a lot of small telescopes and connecting them together with a lot of computational capability in order to search the skies. And so the Allen Telescope Array has been built to do simultaneously radio astronomy searches and SETI. And so we've improved the speed with which we can search for someone else's technology. And more recently, Yuri Milner has provided a grant of $100 million to last over 10 years to fund the Breakthrough Listen project, which isn't building their own telescopes, but they are buying time on large telescopes around the world. They're going to search all the nearby stars. They're going to look at 1,000 stars within 500 parsecs. That's about 150 light years. They're going to look with less sensitivity at 1 million nearby stars. They're going to look at the centers of 100 nearby galaxies, and they're going to look at all kinds of exotic objects that show up on the sky. So they started here at the Green Bank Radio Telescope in West Virginia, building back-end equipment, signal processing equipment, to look at the radio data in ways that radio astronomers do not. They're looking for engineered signals. And they've continued at the Parkes telescope in the Southern Hemisphere. They are also looking in the optical for flashes of light with the automatic Planet Finder telescope at Lick Observatory in California. They are, or they were, they are working with the Chinese at the FAST 500-meter radio telescope, the largest in the world. They're working with the Meerkat Observatory, another large number of small dish arrays in South Africa, and in Jodrell Bank in England. They are building back-end signal processors to look at data from all of these telescopes. Sometimes they're driving the telescopes. Sometimes they're observing commensally, which means that they look at the data that the astronomers are collecting and simply analyze it in a different way, looking for these engineered signals. Until a cable broke and destroyed some of the panels of the Arecibo telescope. They were observing at Arecibo with SETI at home and with other backends looking for engineered signals. Hopefully that will be repaired in the near future and Arecibo will come back online. They're looking with two telescopes that are part of the LOFAR array, low frequency array across Europe and the United Kingdom. Two of the telescopes in Sweden and excuse me, in the UK are looking for SETI signals. There's a group in Italy using a telescope in Medicina to do SETI observations. NASA took one of the Deep Space Network telescopes at Goldstone, California, and put it outside the fence of the Deep Space Network and formed what's called the Goldstone Apple Valley Radio Telescope, which is a project that uses these telescopes to inform and teach students about radio astronomy and the natural sky. And so those students are now doing a sky survey with this Gabbard telescope to look for SETI signals. And another low frequency array in the Western Australia, the Malura Wide Field Array, is also beginning to look for SETI signals. Harvard built a student telescope called the Harvard Sky Survey Telescope, which operated for many years looking for SETI signals on the sky, flashes. All of the data that are collected by the Keck telescope to study radial velocity of stellar lines are reanalyzed to look for engineered signals. There's an optical amateur SETI telescope in Panama, and the Lick Observatory is doing near infrared surveys, and people are looking at archival data that have been collected for other purposes, and they're going back through those data sources looking for evidence of some very extremely powerful transmitters, such as the Kardashev II or Kardashev III civilizations that can make use of the entire energy output of their star for Kardashev II, or the energy output of their entire galaxy for Kardashev III. And so we're looking at archival sources, at old data, to try and see if there's some anomalies that we can pull out that might indicate engineering. In the near future, we've just started using this telescope Veritas, which is 4 different telescopes with an array of photo detectors at their focus. They're intended to find gamma ray sources and excuse me, atmospheric streaks, but we've put new software on this telescope and saying, gee, are there any times that the telescope is triggered by not a range of photodiodes looking at the atmospheric trail, but of Cherenkov radiation, but just single pixels on the sky, the same pixel on the sky with all 4 telescopes that might indicate an engineered flash. And this has just begun operating, looking at archival data and some 30 hours a year of dedicated observing for SETI. There's a project in San Diego called PanoSETI, which is looking to build telescopes that look at 10,000 degrees of the sky all the time. And at the SETI Institute, we're looking at laser SETI, which is using optical, astronomical caliber optical cameras to look at all the sky all the time, if we can, in fact, build something like 15 of these stations around the globe. So we're really trying to look at all the sky all the time and at as many frequencies as we can. So beyond what we're doing just for SETI, there are these fabulous telescopes that are going to be built for astronomical purposes. The James Webb Space Telescope, now called the Nancy Roman Telescope, is hopefully finally going to launch this coming year. And it will be able to look at nearby exoplanetary systems and look for some evidence of someone else's technology, looking for, if you wish, light pollution, CFCs, in the atmosphere, which might be due to technology. Right? I'm sorry, JWST is still JWST. It was the W First telescope that has recently been renamed the Roman telescope. And it's going to check out the technology for a starshade flying independently of the spacecraft, but blocking out the light from the primary star to hopefully allow the light from the reflected light from a planet to be observed and the chemistry of a planetary atmosphere. And then that will be followed sometime in the 2030s, 2040s with a much, much larger telescope. Either there are two designs, Habex or Louvois, to actually have the sensitivity to look at a number of exoplanet systems, to look at their atmospheres for this disequilibrium chemistry that might indicate life. This is a very strange telescope that has been proposed, is being studied by a group in Hawaii. It's kind of a cross between an optical telescope and a radio interferometer for the very, very nearest star system, for the Proxima system. It would, in fact, be able to make an image of Proxima b by following over hundreds of light curves from the orbit of the planet Proxima b and deconstruct it in a way that would allow it to make crude images of the surface of that planet and be able to distinguish continental mass from oceans and actually be able to look for biosignature gases. Beyond that, in the next couple of decades, we're looking at these very large telescopes built on Earth. The 30-meter telescope, the Giant Magellan telescope, the European extremely large telescope, and the Large Synoptic Survey telescope. And we need to figure out how we can piggyback or do commensal observations on these wonderful telescopes, looking for technosignatures rather than just biosignatures. PanoSETI and LaserSETI will come online. The large telescope in China, FAST, is just beginning to take data and is being commissioned. And in South Africa, there's the Meerkat array, which we hope will grow into the first phase of the square kilometer array to give us amazing collecting area for more sensitive radio searches. Perhaps, depending on what the Decadal Review of Astronomy and Astrophysics in the US decides, we may be able to build the northern counterpart to the square kilometer array called the Next Generation VLA. If that EXO Life Finder telescope is ever built and it works, then you could imagine expanding it to this 80-meter colossus, which in fact would have the ability to detect the heat signatures of something like cities on nearby exoplanets. So I like the opportunity to talk to people like yourselves about this project and what we're thinking about, what we're trying to do, because I think it has the effect of holding up a mirror to all of us in the audience and saying, see, all of you, when compared to something else that evolved on another planet orbiting another star, compared to them, you're all the same. All of us on Earth are Earthlings. And I think that message is really important. And that perspective, that more cosmic perspective, putting ourselves into a bigger picture, is extremely important because we're facing challenges on this planet that don't don't respect national boundaries. I mean, we've been reminded of that most immediately, most recently, with this pandemic, which goes all around the planet. And it connects us all. And we are all, in fact, the same. So I'll close this talk with a quote from Caleb Sharp, who's the chairman of the astrobiology department in Columbia University. And Caleb is fond of saying, on a finite world, and that's where we live, a cosmic perspective isn't a luxury, it's actually a necessity. And so if I can give you a homework assignment, I'd like it if you would go to all of your electronic devices and alter your profiles on each of those devices so that the first thing that you say about yourself is that you're an earthling, right? Not a Californian, not a Brazilian, but an earthling. And then the harder assignment is to act like it, because that way we can change the world. Thank you.
Thank you, Dr. Jill. That was a fascinating talk. Thank you very much for this. I wanted to share with you that we had lots of comments in the chat on YouTube, lots of people really excited to see your talk. So thank you for sharing your time with us, and also sharing your time. We know that there are lots of wildfires going on in California. We know that the situation there is not good, and it's really close to you. So thank you for being available despite all of that.
Yeah, one day last week we woke up on Mars. We woke up to an orange sky. So unworldly, really creepy.
Wow. Yeah, we're glad that everything is okay with you. You're safe, and you're here with us today. So, of course, we have some questions here too. So we're going to start with the most obvious one. You talked a little bit about this on your talk, but people want to know, how do you think that the detection of phosphine on Venus changes, how it changes the game on astrobiology? What changed for us in the future directions we might take?
Yeah, well, it's certainly exciting. And just like when the claim was made that inside a meteorite, Allen Hills 84001, there were structures that some people claimed were biological. There was a lot of excitement, and a lot of advance was actually made as we built new tools to examine tiny micro samples of meteorite. I think that phosphine, the discussion about phosphine, will do the same thing. And people are going to write a lot of papers, and they're going to say, oh, you know, in the chemical network that you looked at, you forgot this reaction or that reaction. And it's interesting to me because we found phosphine in the atmosphere of Saturn, and it hadn't had this same kind of discussion. So it's probably the abundance is surprisingly large, and I think we'll make progress. We'll either, you know, verify that there's just no way that you can make this much phosphine without microbial action, or we'll say, oh, yeah, darn, I missed that. There's another chemical pathway that we didn't include. So it's really good that we have these challenges. And it's also important that we understand that sometimes the results are ambiguous. I think technosignatures will probably be less ambiguous if we ever find them. But we need to be open, and we need to show results, even if they're kind of controversial. We need to provide the data. We need to let other scientists look at it from different points of view. So I'm excited by this result, and I don't know how it's going to turn out. We haven't seen the last. I mean, there's the last word has not been spoken on this yet.
Yeah, that's true. Thanks. So moving to the techno signatures that you mentioned. So Lucas is asking, how are the targets for the SETI investigations? How are they selected? How do you select the targets for SETI projects?
Well, for the searches that are targeted and not surveys, we started by looking at the characteristic of the star. So we didn't want it to be flaring or overactive, etc. Then 2011 came along, and we began to get the exoplanets that Kepler was finding. And so we used targets from the Kepler catalog and from radial velocity studies on the Earth that showed that these were stars that had planets. But now, because the statistics tell us that every star has a planet, we basically select them by distance, because the closer stars will be give us signals that are perhaps detectable above our sensitivity level. So yeah, it's evolved over time.
Okay, thanks. So there were some comments saying that SETI is such a thrilling project. People hoping for Arecibo's full recovery, and people really like the analogy also of the glass of water or the swimming pool. That was really cool for us to see. And we have a question here. You briefly showed on one of your slides. So Thiago is asking, can you comment a little bit more about any future plans for collaboration between SKA and SETI?
Yes, SETI has been part of the science case for the SKA over the decades that we've been proposing it, right? And right now, the forerunner of the SKA is Meerkat in South Africa. And so the Breakthrough Listen team at Berkeley is building digital backends for Meerkat. And it will observe commensally, that it is, other scientists will be pointing the telescopes and selecting the frequencies, but Meerkat will be taking the data in parallel and analyzing it for technosignatures. So that's a start, and we hope that that will continue through the Square Kilometer Array.
Okay, thanks. So moving on. Okay, so people are also interested. So we have a question from Iana. What types of signals or signatures do you expect to find at optical or infrared wavelengths?
Well, the kinds of things that we're looking for in the optical and infrared are signals that are highly compressed in time. So flashes that last a nanosecond or less. Now, if you think about how much material you can pack into a sphere that light would travel across in a nanosecond, it's not much, right? So naturally, it would be very difficult to get a coherent pulse like that. You can do it with technology. We've got lasers and you can do that. The other thing that we're looking for in the optical is a monochromatic signal that might be indicative of a laser at one particular frequency. So now that we're thinking about projects like Breakthrough Starshot, where they're talking about building this gigantic laser to accelerate a little postage stamp spacecraft to 20% the speed of light. That kind of huge, powerful laser would be detectable and would certainly outshine the star that the planet was orbiting by many orders of magnitude. So both kinds of things, monochromatic laser signal and very short optical pulse.
Okay, great, thank you. So we now have curiosity from Karim. In 1977, there was a radio signal, the WOW signal, at Ohio State's Big Ear radio telescope detected. So was it ever established what it was?
No.
No, cool.
People have looked back at that area of the sky for various reasons. It's a bit ambiguous exactly where that signal came from. We've spent a bunch of time looking at it with the Allen Telescope Array. No, it's never repeated. And in fact, I like to say that if I had been running the Ohio State Radio Telescope project at that point, you would never have heard of the WOW signal because it failed the test that they had set up to verify the signal. There were essentially two beams on the telescope, an east beam and a west beam, and the signal came up in one of the beams and then died away and failed to show up in the other beam. So it failed the verification process that they had established in advance. So I would have said, nope, didn't make it. You'd never have heard of it.
Cool, thanks. So, okay, then we have lots of thank yous and wonderful talks. So people are really, really excited with your talk. So thank you again. And okay, so now moving on to a more personal question. So if you had infinite funds, how would you search for life?
Oh, well, infinite funds.
It's a dream.
Well, we're stuck at any point in time. We can't do what we haven't invented yet. So we have to admit, with respect to searching for technosignatures, that we may be doing a fantastic job at exactly the wrong thing, right? Because there's some technology that we haven't yet invented that is the appropriate one for interstellar communication. And, all you can do with respect to that is to stay around long enough, solve the problems on this planet so that we do have a long future. And then when that technology is eventually invented, if it makes sense for interstellar communication, then include that in your searches. Continue to do what you've been doing, but also include these new capabilities. One such thing is artificial intelligence. So all of the searches to date have asked a computer to look at data from an optical telescope or a radio telescope and ask if they can find a pattern in frequency and time which has particular characteristics. But now with artificial intelligence, we're getting to the point where we can expose a computer to data and simply ask us, is there anything anomalous in there? Not just, is it a particular pattern, but tell us if there's anything that has information content in there. So that's something we haven't been able to do in the past. We can't quite do it yet, but we will within a few years be able to do that sort of thing. And so that's a new capability. But we just have no idea about what we don't yet know. What technologies might we have access to in the future that might lead to success? we're stuck with what we know, and we reserve the right to get smarter.
It's nice. So we thanks for that answer, and we have two more questions. So the first one is, where from Luis Felipe Menezes, where in the solar system do you think we are most likely to find life?
Right. So people are sort of in two camps here. All right. There's a group that says subsurface liquid aquifers on Mars. Good place to look. Another camp says, life started probably in the oceans on this planet. So the oceans beneath the ice of Enceladus, for example, is a good place to look, or Europa. And we're going to explore those for all kinds of different reasons. And I'm very eager to see what the results are. But, because of the potential that we now recognize for life in these environments, the way that we explore these places has to change. We have to make sure that we don't introduce the life that we find, right?
Yeah.
So when it was just the surface of Mars, which is pretty hostile environment, we don't think life can survive there, are the rules for how much of a bacterial load we can take to Mars was one thing. But now when we want to explore these potentially wet regions, we've got to do a better job, because we don't want to, you find life on Mars and you have to ask the question, is it related to us?
Okay, thanks. So moving on to the last question we have here. So this from Thaisa. How far could we detect signals of Earth with Earth technology of today?
Well, the strongest signal that we produce at radio wavelengths is a planetary radar associated with the Arecibo telescope. And that could be detected halfway to the center of the galaxy. If you talk about the most abundant signals, because that radar isn't used very often and it would have to be pointed right at you to detect it. But if you talk about the most abundant leakage radiation from the Earth, those are radio and television transmitters. And there, the power is so much lower because you're trying to illuminate the neighborhood, not the nearest stars. So, in fact, barely detectable at the distance of the nearest stars, our leakage radiation. Okay. With today's telescope, when we get the square kilometer array or the next generation VLA, different game. Okay, thank you. So that was the last question. But if you don't mind, I would like you, I'd like to make my own question and to ask you for an overview. So you've experienced the whole field of astrobiology since the 60s and the beginning of SETI, and you've seen it all. So it's a kind of a two-part question. Did you expect for us to be where we are right now in 2020 in terms of knowledge when you started in the field, and where do you expect we will be in another 60 years? Yeah, certainly I'm surprised by the result that we can now say every star has a planet. I mean, when we started, we didn't know about any planets other than our own solar system. And so actually it was SETI and SETI workshops that started the whole field of exoplanet detection. We brought in people and started to have workshops saying, how the heck are we going to figure out whether there are any other planets out there? And fortunately, that went forward in a way that didn't suffer the roller coaster political funding attacks that SETI itself did. So, I'm surprised by that result, and I'm also surprised because when we started to try and build planetary systems in computers as modeling, they all somehow turned out to be just like ours. Little rocky planets in circular orbits near the star and big gas giants outside. And what's so startling is the amazing diversity of planetary system architectures that we're finding out there. And that's cool. I mean, it just shows us how unknowingly biased we were when we were trying to model things in the past. So I'm delighted to find that nature is a lot more inventive than we are. The extremophiles are also totally wonderful. We in 19 wow, when we started this business, 1970s, who could have imagined a black smoker? Who could imagine life at the bottom of the ocean where the crust is splitting apart and the water is superheated and life is thriving, right? So I'm delighted that we're being knocked off our pedestal. We've sort of had this the ascent of man, right, as being the end point of evolution, and that terrible bias. And evolution doesn't work that way at all. We're not special. We're just one tiny twig on an enormous tree of life. And so extremophiles have made us rethink our prejudice and our privileged place. Life is just so much more clever and abundant and than we could have imagined it all those years ago. So, both of these things, the exoplanets and the extremophiles, over my career, it's made the universe appear to be more biofriendly than we once might have thought. And now our job is to go find out whether, in fact, it is. So that's the next 60 years, right?
Okay. Thank you very much for the answers and the fantastic talk. So you should know that some people comment that they already changed their profiles on the social media to include the Earthlings. So you should know that. Sorry?
Now the hard part is act like it.
Yeah, they act like it's the difficult one. So we will end the live broadcast now. We will return to the private broadcast, but I wanted to thank you again for this fantastic talk and being here with us. It's a huge honor for Valongo Observatory, which is the Astronomy Institute of Federal University of Rio de Janeiro. And we hope whenever you want to come back and dance some samba again, when it's possible, you are more than welcome to visit us, and we can talk in person again when it's safe to do so. But meanwhile, thank you very much. It was a great honor and privilege for us to have you here with us.
Well, thank you for having me. And yeah, when we get back to normal, can dance the samba again. That sounds like a great invitation.
Great. Thank you very much, Dio. Thank you very much, everyone who attended the talk. Next week, we'll be back. Check our schedule in our website, the Valongo website. So, and thank you very much. You should subscribe to our channel because we schedule the talks in advance so you can get the reminders to see the next talks. Thank you very much, everyone. Have a great afternoon. See